Hey everyone, this is the third slide video on the fluid mechanics. I'm going to talk about the extra problems in the back. So this first one we have, it's basically related to up. We want to know how many helium balloons need to be there are needed to lift a small house. That's about 46,000 kilograms. We're going to assume that each balloon has a diameter of 33 centimeters. All right. To make your life easy, we're going to ignore the mass of the balloons and the buoyant force on the house since those are mostly going to be negligible. So you could pause the video and we'll go over it in a second. All right. So this is just using the buoyancy part that we used in the first video. So what we know is the buoyancy force on the balloons is going to be equal to the weight of the house plus the weight of the helium. And that's going to go to rho VG, that's the weight of the air being displaced by the balloons, and that's going to be equal to the combined weight of the house and the helium. Now, I said the mass of the balloons is in the rubber part of the balloons. So if we take these two terms, move it over here, we end up we can also rewrite the volume of the helium to be the number of balloons times the volume of one balloon, 4/3 pi r cubed. Getting rid of the g, we also got rid of the g's here, and we end up getting this relationship. We can simplify, we could plug in our numbers, moving things around, solve for n, and we end up getting 2.2 times 10 to the 6 balloons. So a very, very significant amount of balloons. I believe that's 2.2 million balloons. All right, so this one is an interesting problem. It's based off of Bernoulli. It's a derivation of Bernoulli's. So it wants you to come up with this relationship of dH over dt. Now, one hint that I'll give you is that you're not just going to use Bernoulli's. Think about an equation that uses area. And also think about, what do you get when you do a height divided by a time? All right, so pause the video, work on this yourself, and we'll go over it in a second. All right, so the big hint here is that this is referring to speed. So the idea is that we're going to use Bernoulli's equation and simplify it so that we're solving for speed, putting everything to one side except for the one speed term. And then also, because I have area here, that means I'm going to want to do something with flow rate, AV equals AV. So the first thing I'm going to do is I'm going to take the Bernoulli's. Now, same thing as before. Both ends of the vat are exposed to the same air pressure, so these P1 and P2 can drop out. I'm going to combine this rho g y1 over to here, and then just have it so that it's h instead of the y2 and y1. And I'm going to move this velocity over to here. So I end up getting this. 1/2 of the difference in the speeds equals gh. Again, I could also get rid of the densities once I get rid of the pressures. Like I said, one thing I want to do is I want to rewrite one of these velocities into like terms. So I'm going to take, doesn't matter which one, take V1 and replace it with V2 over the ratio of the areas. That's coming from that continuity equation, the flow rate equation. Plugging that in over to here and pulling out the V2, I can then move this over to here. We'll have to do some simplifying, rewriting this A2 over A1 squared minus 1 as A2 minus A1 over A1. Move it over to here, put it underneath, and then square root both sides, and we get this. So as we can see, it's already very similar to what they wanted. However, one thing to note is that there's a negative sign here. Well, that negative comes from the fact that the water is decreasing. So what we're going to say is the height is going down. So that's where that negative comes from, and we get exactly what they wanted. All right, so for part B, they want us to integrate this as a function to determine h as a function of time. And then part C, we're going to plug numbers in to actually figure out how long it takes. So pause the video, work on this yourself, and we'll go over it in a second. All right. So in the first part, integrating is pretty self-explanatory. So what we have is this term. What we need to do is get this h term over to here, and then we could throw the t over to here. The nice thing is that there's no other terms besides this single h. So when we do that, we're going to integrate both sides. In here, we're going to integrate essentially h to the negative 1/2. And then this one is just integrating dt. Here we're going from h0 to h and 0 to t because of what they set up here. Now this has a very easy integration. It ends up just being this, essentially 2 rad h. Yeah, I'm not going to explain the integration part. And then this one's just regular t. Don't have to worry. Again, very easy integration there. Getting h by itself, we take this, bring it over to the other side, and we end up getting this as our relation. And then since we want to know what h is by itself, we have to actually square this entire thing. Now, note that does not mean that I'm getting rid of these square roots. I have to square this entire term. So I end up getting this. So this is my height as a function of time. Now for part C, I'm just going to take the numbers and just plug them in. Easy peasy. They give us the radius, right? Yeah, the diameter. So that's going to give us the cross-sectional area. So we can use these numbers to find all the other things that I'm looking for. Like we know that it's going to empty, so h ends up going to 0. We know its initial height is 10.6 centimeters, so it goes to 0.106 meters. I'll plug the numbers in, and we figure out that the time ends up being 92 seconds. So it's going to take 92 seconds for the entire vat to empty. All right. Believe that's it. So if you have any other questions when it comes to these fluids, let me know, and we'll go over it maybe during the next recitation. All right. See you all later.